In the last video, we were talking about differential equations, which looks something like this. Y dot over x dot is equal to some power series in terms of x on the right-hand side. For example, x squared plus x cubed, or something like this. And in this video, what I'd like to do is show you how Newton is going to outline how we're going to solve differential equations, which look something like this. Y dot over x dot is equal to x plus y, where we now have x's and y's on the right-hand side of the differential equation. And we're going to tackle this equation, and we're also going to tackle the differential equation y dot over x dot is equal to y. And along the way, by solving this differential equation, we're going to find the power series for another very useful function, which is e to the x. As is the theme in this video series on the method of fluxions, we're going to attempt to solve this problem, to solve this differential equation, by means of a power series. What we're looking for is some y, which is going to be written as a power series in the x's, which solves this differential equation. That is, its derivative is the same thing as itself, which is what this differential equation is saying. That is, this y is invariant under taking a derivative with respect to x. And what I'm going to do, before I get to how Newton is going to suggest that we solve this differential equation, is solve it by a means of iteration or of guessing. What I'm going to do is take a guess as to what the first term of this power series is going to be. And it turns out I have some freedom in doing so. And what I'm going to do is I'm going to say the first term, that constant term of that power series, is 1. Now, in the language of differential equations, what I'm doing here is I'm applying the initial condition that y of 0 is equal to 1. Now, I could have just as easily picked 2 or 3 or any other value, but we're going to see that we can derive one solution to this differential equation by making this assumption. Now, this function has to have the property that on the left-hand side, its derivative is the same thing as itself. So what is the derivative of what I have written down here so far of 1? That's going to be 0. So on the left-hand side, I'm going to write 0. Now, what is y equal to so far? It's equal to 1. Now here, we see that the two sides of the equation are not equal. So what I'm going to attempt to do on this left-hand side is correct the deficiency that I see. And what I see is I need to add 1 to the left-hand side of this differential equation. Now, if I'm adding 1 on this side, this is the derivative side, what has to be added to the y side of this differential equation such that when I take its derivative, going over to the left-hand side, I get 1. In other words, what is the antiderivative of plus 1? And so the answer to that is x, positive x. So that's what I'm going to do next. I'm going to add this additional correction factor of x. Now I repeat the same process. On the right-hand side, I now have 1 plus x. Now I take the derivative of 1 plus x, and now on the left-hand side, I get 1. Now you see that these two sides are still not equal to each other. This side here has that additional plus x, so that's what I'm going to do. I'm going to attempt to correct that by adding plus x on the left-hand side. Now, what is the antiderivative of plus x? That is, what had to be added to this to create that plus x? The answer to that is going to be x squared over 2. And hopefully you can see how this argument is going to start to play out. The next term in this series is going to be given by taking the antiderivative of the term just before it. I got this x by taking the antiderivative of 1. I got the x squared over 2 by taking the antiderivative of x. So I'm going to get the next term by taking the antiderivative of x squared over 2, which is going to be x to the third over 3 times 2. I take yet another antiderivative. I get x to the fourth over 4 times 3 times 2. And hopefully you can see the pattern that we're starting to form here. That is, let me rewrite this y so that the pattern is clear. I have 1 plus x squared over 2. Not just 2, I'm going to write 2 factorial, even though 2 factorial is indeed equal to 2. Now for the next term, I have x to the third over 3 factorial, because 3 times 2 is equal to 3 factorial. And then the next term is going to be given by x to the fourth over 4 factorial, and so on. And if I wanted to very compactly express this infinite series, I could write it like this. Y is equal to the infinite sum, letting n go from 0 to infinity, of x to the n over n factorial. Let's now verify that this y that we just found solves this differential equation. That is, that its derivative is equal to itself. So let's find that derivative. So we have y dot over x dot is going to be equal to, and we're going to take the derivative term by term, as we have been doing. The derivative of 1 is 0. The derivative of x is 1, so I have 1. The derivative of x squared over 2 factorial is going to be x. X to the third over 3 factorial. If we have a look up here, we see that the 3 comes to the front, cancels out the 3 down there. That's going to be equal to plus x squared over 2 factorial. We find the derivative of x to the fourth over 4 factorial. We're going to see that that 4 comes down to the front, cancels out the 4 down there. And we have x to the third over 3 factorial. And hopefully at this point you can see what's going on here. That upon taking the derivative, we get the function itself, what we started with. So indeed, this power series that we just found is one solution to this differential equation. And this particular solution to this differential equation, where upon plugging in x equals 0, we get y is equal to 1, gets a very special name in calculus. This power series is called e to the x. Also this one down here, written in sigma notation, e to the x. And it has that important property that y prime is equal to y, or written in more modern notation, d over dx of e to the x is equal to e to the x. So we've just found a very important power series that's going to be used all the time in calculus and differential equations. I would now like to show you how Newton has this tabular method for finding the power series solution for differential equations. And we're going to work with the following differential equation to see that. Y dot over x dot is equal to x plus y. Pretty similar differential equation, but different solutions. And here's what we're going to do. I'm going to draw out this table, and what I'm going to do, in this space over here, I'm going to write down anything. If I see any terms that involve a y, I'm going to write them there. So I see a y there, and next, underneath it, I'm going to write a space for the sum. And this will all become clear once we start doing the procedure. And below that, I'm going to write y is equal to, I'm going to have some stuff over here eventually. And in this upper space over here, I'm going to list out all the other terms. So I've already written down the y, and now what I'm going to do is write down the x. And here's what I'm going to do. I'm going to arbitrarily pick some first term for that constant term there, just like I did in the previous example. For example, let's pick 1. So y is going to be equal to 1 so far. And whatever I have down here, y is equal to 1, I'm going to write that up here. Y is equal to 1. This sum is going to be the sum of all the stuff in this first column here. This is going to be like the 0 degree column, the constant term column. So I see that the sum of all the stuff here is 1. Now here's the next step. In this sum position, sum is equal to 1 so far, I'm going to look at that 1, and I'm now going to take the antiderivative and write it in this next position here. And so now I have 1 plus x. And I'm going to copy that x up here. So you see that whatever I start to write down here, I'm also going to write up here. Now I'm going to sum all the stuff in this first degree column here. You see that I put these two together because they're of first degree. And I see that the sum is 2x. And now I'm going to take the derivative or the antiderivative of 2x, and that's now going to give me x squared for the next term in y. So now I'm going to copy that up there, plus x squared. The sum of all the terms in the second degree terms here is still x squared. And I just repeat this procedure. Take the antiderivative. Next term becomes x cubed over 3. And hopefully you can see that the successive terms are going to be derived by taking the antiderivative of the previous term. So the next term is going to be x to the 4th over 4 times 3. And the next one is going to be x to the 5th over 5 times 4 times 3, and so on. Let's now verify that what we've gotten out of this method is actually a solution to this differential equation. That is, that taking the derivative of this thing on this left-hand side is the same thing as adding x to it. That's what this differential equation is saying. So let's find, well, first let's do the easy thing, which is add x to this thing. When I add x, that's just going to boost that term by 1 unit. So I'm going to have 1 plus 2x plus x squared plus x to the 3rd over 3 plus x to the 4th, 4 times 3, plus x to the 5th over 5 times 4 times 3, and so on. Now, let's take the derivative of this y. We have y dot over x dot. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x to the 3rd over 3 is x squared. The derivative of x to the 4th, 4 comes off front, cancels the 4 down there. We have x to the 3rd over 3. The derivative of x to the 5th over 5 times 4 times 3, 5 comes out front, and we're left with x to the 4th over 4 times 3, and so on. We have those higher order terms there. And you can see, comparing term by term, that indeed y plus x is equal to y dot over x dot, which means this y that we've just found is one solution to this differential equation. And it happens to have the initial condition that y0 is equal to 1. In other words, the point 0, 1 is on this curve. In addition to finding that one particular solution to this differential equation, this method will allow us to calculate the general solution to this differential equation. And the way we're going to do that is, instead of actually selecting one particular number for that first constant term there, I'm going to leave it as arbitrary. Let's just call it a. So I'm going to stick some arbitrary value, a, as that first term. And I'm just going to run through this procedure. I have that first term a there. The sum of all the stuff in that first column, the 0 degree column, is still a. I find the antiderivative of a. That's going to be a times x. I copy down that ax up there. I now see that the sum of all the stuff in the first degree column is going to be, we have ax plus x. So let's not plug plus there. It's going to be a plus 1 times x. And now I take the antiderivative. I find that the second order term is going to be a plus 1 times x squared over 2. And then I'm going to end up copying it down there. The sum is going to be precisely the same, which means that the next term, the third degree term, can be found by taking the antiderivative of this term. And the same is going to be true for all the higher order terms. So the next term is going to be a plus 1 times x to the 3rd over 3 times 2. The next term is going to be a plus 1 times x to the 4th over 4 times 3 times 2, and so on. And now, what I'd like to do is rewrite this in a slightly different way. I'm going to have y is equal to a plus ax, but now I'm going to distribute all of these terms that contain the a plus 1 there. I'm going to write one copy as ax squared over 2. Now I'm going to write 2 factorial. I'm allowed to do that because 2 factorial is the same as 2. That's when I distribute a to x squared. And now in this term here, I'm going to distribute a to x cubed. I'm going to get a x cubed over 3 factorial. And now I'm going to distribute the a to the x to the 4th. I'm going to have a times x to the 4th over 4 factorial, and so on. And now, the only other terms I need to take care of are the 1s being distributed to each of those terms there. So now I have plus x squared over 2 factorial. And I'm going to distribute the 1 to the x cubed there. And notice how I'm keeping everything in order. I'm kind of lining up the terms, because you'll see what I'm going to do next. I have x to the 3rd over 3 factorial. Then I have x to the 4th over 4 factorial, just distributing that 1 to the x to the 4th, and so on. And now I make an observation that this upper line that I've written here is equal to a times e to the x. After all, you can see that after we've just derived what e to the x is, it's just being multiplied by a out front. So that takes care of this upper line. This upper line is a times e to the x. But what is this lower line equal to? Now it almost looks like e to the x, except it's missing, let me draw these terms in here in parentheses. It's missing an x, and it's missing a 1. So this is not e to the x, but it's e to the x subtracting away x, and also subtracting away 1. And hopefully you can see here that what we just derived, y is equal to a e to the x plus e to the x minus 1 is the general solution to this differential equation. And I'm going to rewrite this as y is equal to, I'm going to combine these e to the x's. I'm going to get a plus 1 times e to the x minus 1. And this right here is the general solution to this differential equation. And one last thing I could also notice is if I plug in the particular value, where a is equal to minus 1, that's going to get rid of this first term here, because I'm going to have minus 1 plus 1, which is 0. I'm going to have 0 times e to the x, which is 0. And what that tells me is that y is going to be equal to minus x minus 1. And this particular solution to the differential equation is going to have the initial condition that y of 0 is going to be minus 1. In other words, the point 0 minus 1 is on this curve. And indeed, you can see that if I have this equation, y is equal to minus x plus 1, that its derivative, y dot over x dot, is minus 1. But also notice that taking y and adding x to both sides of the equation also produces minus 1. These two agree, which verifies that this is indeed a solution to this differential equation. We can also notice that if I take a look at this constant sitting out front of that e to the x, which is a plus 1, I could rename this as another constant. Let me call it c. And I could just as well rewrite this general solution in the following way. Y is equal to some constant c times e to the x minus 1, which is probably something you would more commonly see as a way of writing the general solution to a differential equation like this, which is, it's also called a first order linear ordinary differential equation. I'd like to show you one last example using that tabular method that Newton uses. how to solve the following differential equation, which Newton talks about in the text, which is y dot over x dot is equal to 1 minus 3x plus y plus x squared plus xy. And let me show you how we're going to write out this table. Again, in this space here, we're going to write out any term that involves a y in it. And in this differential equation, we have two. We have this y here, and we have the x times y. So I'm going to write down a space for the y, a space for the x times y, and then just below that, I'm going to write the sum. And then finally, I have y is equal to the developing power series in this region here. And then these remaining terms, which involve x's only, the 1, the minus 3x, and the x squared, I'm going to write them in the appropriate columns based on their degree or their order. I have the 1, that's going to be the 0 order term. Next, I have the minus 3x, which is going to go in this first degree column here. And then I have x squared, which is going to go in the second order term there, or second order column there. And now I'm going to carry out the same procedure to find the general solution of this differential equation. I'm going to let that first term for y be arbitrary. Let's call it a. Now I'm going to copy that a up here because so far I have that y is equal to a. But notice here I have this second row here that I'm going to have to deal with. And so far what I have is that y is equal to a, but upon multiplying by x, I get ax, which is going to be written in that first order column there. And now I do the same procedure. I sum all the stuff in this column. In that case, we had 0 there. So I sum all the stuff, and I get a plus 1. And now I take the antiderivative of a plus 1 to find a plus 1 times x as the next term in the power series. And now I take that term, I copy it up here. I have a plus 1 times x. But since in this row it's being multiplied by x, that's going to move over here. I have a plus 1 times x squared. Squared because it's getting multiplied by the additional factor of x. And now I sum all the stuff in this first order column. So I'm going to have minus 3 plus a plus 1. So far we have a minus 2 plus an additional a right there. So I'm going to have 2a minus 2 times x. And now I do as I usually do. I take the antiderivative of that. The 2 is going to divide this coefficient here. So I'm going to get just a minus 1 times x squared after simplification. And now just carry out the procedure as you see here. And up there I have a minus 1 times x squared. And over here I'm going to have a minus 1 times x cubed. I sum together the stuff here, and I'll stop here, and I'll leave the rest for you as an exercise. So carry on this table, and additionally, check that what you're getting out of this procedure for y is actually a solution to this differential equation. That is, calculate the derivative, and make sure it's equal to 1 minus 3x plus y plus x squared plus xy. That'll wrap it up for this video. Hopefully you've enjoyed seeing how certain differential equations can be solved using these power series methods. And if you already knew that such a thing could be done, that we could solve differential equations with power series, hopefully you've appreciated this more historically accurate development of such a method. And hopefully you'll join me for the next video on the method of fluxions and infinite series. If you enjoyed the video, feel free to subscribe to my channel, like the video, and comment. And thanks for watching.